A heat pump system does not generate heat. It moves existing ambient heat from one place to another. That single distinction is the source of its efficiency advantage over traditional combustion heating. A gas furnace burns fuel to create heat, converting the stored chemical energy exactly once. Even the best modern condensing furnaces hit a hard physical limit. They peak at about 95 to 98% efficiency, yielding at most 0.9 units of heat for every unit of fuel consumed. They are permanently bound by the energy density of the fuel itself. A heat pump also requires an input, electricity. But that electricity is not burned to create warmth. It is used to power a mechanical compressor. The electrical energy drawn by the compressor is the cost of transport. It is the power required to physically move thermal energy from the outside environment into the building. Because the environment already holds that thermal energy, even in cold air, the system bypasses the once-through conversion limits of combustion. Decoupling heat delivery from fuel combustion is the mechanical distinction that gives heat pumps their thermodynamic advantage over furnaces. To understand how this thermal transport works, we look at the closed refrigeration cycle. A continuously circulating chemical refrigerant acts as the vehicle for the energy, and the process starts here, at the compressor. This diagram illustrates the first thermodynamic phase. The compressor draws in the refrigerant vapor, driving up its pressure. As pressure rises, the gas temperature spikes. That hot, high-pressure gas flows to the indoor condenser coil. Here, it releases its heat into the building. As the thermal energy leaves the refrigerant, the gas condenses into a liquid. The liquid then reaches the expansion valve. It passes through a bottleneck, undergoing a rapid pressure drop that causes its temperature to plummet. The supercooled liquid finally enters the outdoor evaporator coil. Because the liquid is colder than the outdoor air, it absorbs heat from the surrounding environment. This thermal absorption vaporizes the refrigerant back into a gas, and it returns to the compressor to repeat the cycle. On the indoor side, the useful output of this cycle is physical warmth delivered into a room. By manipulating pressure to force chemical state changes, the system successfully moves heat against its natural thermal gradient, pulling warmth from cold air and delivering it at a higher temperature indoors. Engineers measure the efficiency of this transport mechanism using a specific metric, the coefficient of performance, or COP. Look at this chart. It defines COP as the ratio of heat delivered to the building divided by the electrical energy used to drive the compressor. Here, 1 unit of electricity yields 3 units of thermal output. That is a COP of 3. Compare that directly against a top-tier gas furnace. 1 unit of fuel input yields at most only 0.98 units of thermal output. A COP of 3 to 5 often triggers what looks like an efficiency paradox. Delivering 3 kilowatts of heat for every 1 kilowatt of electricity drawn seems to violate the conservation of energy. It does not. The additional 2 to 4 units of energy are harvested from the ambient outdoor environment. They are transported, not created. Even when factoring in the transmission losses of a gas power plant running at 50% efficiency, using that electricity to run a heat pump with a COP of 3 delivers more useful heat than burning the same gas directly in a residential furnace. Measuring the coefficient of performance shifts the engineering focus away from the limits of fuel energy density and squarely onto the mechanical efficiency of thermal transport. The primary thermodynamic limitation of a heat pump is governed by the Carnot principle. Efficiency drops as the temperature difference between the outside source and the inside delivery grows. This difference is called the temperature lift. Extracting heat from sub-freezing air and elevating it to a comfortable room temperature requires the compressor to work harder. As outdoor temperatures fall, the COP naturally decreases. This physical reality led to a historical misconception that air source heat pumps fail entirely in extreme cold. Modern regulatory standards tell a different story. U.S. Energy Star Cold Climate Certification requires units to maintain a COP of at least 1.75 at minus 15 degrees Celsius. Field data from leading product lines shows that modern units maintain heating capacity down to minus 25 degrees Celsius. A properly insulated thermal envelope ensures the building retains this transported warmth, contrasting with the freezing exterior. To maintain efficiency, systems manage ice accumulation on the outdoor evaporator coil through a defrost cycle. The unit will briefly reverse flow, sending hot refrigerant back outside to melt the frost before resuming normal heating. The performance of these systems in freezing conditions is best demonstrated by adoption rates in the Nordic countries. These regions maintain the highest per capita heat pump use globally, despite winters that regularly drop well below -20 degrees Celsius. Operating at a high temperature lift in freezing conditions is an established engineering standard. What specific internal advancements enable this performance in freezing conditions? The first factor is chemical. Under the Kigali Amendment, the industry is phasing out high global warming refrigerants like R410A. In response, manufacturers transition to the A2L class of refrigerants like R32. Aside from a lower global warming potential, their distinct pressure properties improve the operational range of modern equipment. The second factor is a critical hardware upgrade, the variable speed inverter-driven compressor. Older systems operated on a fixed capacity, cycling on and off to maintain temperatures. Inverters, by contrast, continuously modulate their output speed. This continuous modulation allows the system to match the building's fluctuating thermal load, drawing exactly the power needed and maximizing seasonal efficiency. The combination of A2L chemistry and inverter-driven mechanics allows modern systems to squeeze thermal transport out of minimal electrical input. The principles of thermal transport apply to the requirements of heavy industry. International Energy Agency data shows that industrial heat pumps achieving a COP near 3.5 are now cost competitive with gas. They are currently viable for large-scale processes that require heat below 150 degrees Celsius, including pasteurization, drying, and low-temperature chemistry. The next technological leap relies on transcritical carbon dioxide heat pumps. Using CO2 as a natural refrigerant sidesteps phase-out regulations and allows researchers to push delivery temperatures toward 300 degrees Celsius, a threshold that covers a large share of industrial process heat. The core thermodynamics of manipulating pressure to move ambient heat scale to meet the thermal demands of the global supply chain. While the underlying science is settled, three logistical barriers continue to slow widespread global adoption. The first is upfront capital cost. A typical cold climate installation in the US runs between $10,000 and $20,000, compared to $3,000 to $6,000 for a standard gas furnace. The second is retrofit complexity. Heat pump delivery temperatures match with low-temperature underfloor heating, but installing them in older homes requires matching the system to high-temperature legacy hydronic systems. The final barrier is a workforce bottleneck. The installer workforce has spent decades training on gas equipment, and retraining technicians to handle high-pressure refrigerant cycles will take years. The hurdles facing modern heat pump deployment are found in market and engineering logistics. The underlying thermodynamics are already established. For a full technical data breakdown, equipment reviews, and detailed field reports, visit the platform directly at ProReadyEngineer.com.